Hi, my name is Dr. Alex Macknow, and it's my pleasure to welcome you to this lesson, Lesson 4.1, in which we'll explore some of the basics of Skill 4 questions. As the first lesson in this chapter, this may very well be your first exposure to this type of question. Skill 4, as identified by the AAMC, is data-based and statistical reasoning, or data analysis for short. And just because this is the last of the skills identified by the AAMC, don't misconstrue that to mean it's the least important. In fact, these questions will account for 10% of those that you see on test day and are an important contribution to your score on the exam. These questions tend to ask you about interpreting figures, graphs, and tables, or thinking about the relationships between variables and how they might be represented. They may ask you to think about systematic and random error within research, or they may ask you to draw statistical conclusions, thinking about things like measures of central tendency, standard deviation, and variance, as well as statistical significance. Well, in this lesson, we'll restrict our focus to the first two of those tasks, namely interpreting figures, tables, and graphs, and thinking about the relationships between variables and how those can be represented. We'll also think about the conclusions one can draw from those figures, tables, and graphs. So with that, let's take a look at our learning goals for this lesson. We'll start by interpreting those graphs, charts, and tables and mining them for the important findings that they demonstrate. We'll then go the other direction by finding the relationships between different variables and finding appropriate graphical representations of that same data. Finally, we'll think like a scientist, and this is what makes this lesson fun. We'll then use that data to determine some of the conclusions one could make from the study and make predictions about what might happen under different conditions. This is indeed how you'll think as a physician as well, when you interpret research papers on the wards, when you attempt to apply that information to a patient who doesn't quite fit the study criteria that are presented. Indeed, this is why this information is included on the MCAT, because it's applicable to your future career as a physician. Our science topics from this lesson come from behavioral neuroscience, specifically sensory processing and the biological bases of behavior. In that latter category, we'll be looking in particular at sleep. No worries though, we're not going to put you to sleep with this content. Rather, we'll keep it interesting enough and test day relevant to make sure you perform well on these Skill 4 questions when you hit the exam. Remember, the focus during this lesson will not be on covering all of this content that shows up other places in your MCAT resources, but rather using it as a launching off point to be able to see the application of this material within Skill 4 questions. So let's start out with the first learning goal, in which we'll take the visual representations of data and we'll determine what trends or findings are relevant there and interpret that information. Let's start out with the first experiment. Like many experiments on the MCAT, a lot of key information is given in the first sentence. We're given who is doing the experiment, which is almost always an important part of the study. It could reveal potential bias, or if it's a student, the need to look out for mistakes. We're told what this individual is trying to figure out, what the goal is of this study. In this case, the neuropsychologist is looking at a lesion in the reticular formation. We're told that that's a part of the brainstem, and the connection between that and how long a patient spends in a particular sleep stage. We're also told what this individual measures, and that's going to be time. We're looking at how long that patient is in that sleep stage. So to look for this association, the neuropsychologist invites 6 individuals with this kind of lesion to participate in a sleep study. And we see this information presented to us in Table 1. When you see a table on the MCAT, there are a few important things to look for. First, identify what the rows and columns refer to. In this case, the various rows represent different individuals, person 1 through person 6, and the various columns are representing amounts of time, the hours spent in each of the major non-REM sleep stages, and REM 1 through 4, the amount of time spent in REM, and then the total amount of sleep. And actually looking at these individuals, you may be a little bit jealous. As a pre-med student, you probably don't have the opportunity to have 10.7 hours of sleep each night. Then look for general trends that you see within the table. Taking a quick glance at the table, what sticks out to you here? What is interesting within this table? Well, there are a few things that could be pointed out, but probably the most important is the fact that the amount of time spent in REM sleep is significantly larger than all of the other stages. In fact, it accounts for almost as much time as the other stages combined. It's almost 50% of the time these individuals are spending in sleep. You wouldn't want to overanalyze this table. That's enough information just looking at the major trend that's presented, and spending significantly more time looking at each table entry would be a waste of time. The MCAT is unlikely to ask you more than one question on this table, and if it does ask a question on the table, it's likely to be about the most predominant or most notable trend that exists within it. So with that, let's take a look at a Skill 4 question associated with this table. In this first question, we're asked to analyze the data in that table, specifically looking for the stage of sleep in which participants spent the most time. And this should be a slam dunk. It was the predominant trend that showed up in the table. It was the major thing that we identified when analyzing the table, so it should be a quick match. Participants here spent the most time in REM sleep. In fact, that's true for all 6 participants in the study. Not all questions that ask you to analyze a data table are quite such a slam dunk. But still, the appropriate first step when presented with a data table is to identify what the rows and columns refer to and identify the major trend that exists within that table, and then move forward in the passage to get yourself to those questions. So let's continue following this neuropsychologist's study. After gathering some data on the 6 individuals with a lesion, the researcher then compared the time that each participant spent in REM with control counterparts, those being individuals who do not have that same lesion in the reticular formation of the brainstem. So the researcher moved from analyzing a particular group of 6 individuals to now comparing 2 groups and presents that information in Figure 1. Take a look at Figure 1. It's a stacked bar graph, and when presented with data like this, we'll do some of the same things as we did during table interpretation. Start again by identifying the axes. In this case, we have time on the x-axis given in 2-hour intervals, and on the y-axis, it's categorical information. We're comparing individuals without the lesion to individuals with the lesion. So take a look at the information presented in the bar graph. What do you notice about the data here? Again, there are a few possible observations, but the most important trend to note is that while the amount of REM time increases significantly from having no lesion to having a lesion, in fact it almost doubles the amount of time in that sleep stage, the amount of non-REM time is about the same. If we look, it's about 6 hours regardless of if the individual has the lesion or does not. So to summarize the information here, we see a big increase in the amount of REM, and by extension the total amount of sleep, whereas the other sleep stages, non-REM sleep, is still approximately the same. We've seen one question already that asks us to interpret the information from a table, so let's see another question that asks us to interpret this figure instead. In this question, we're given a good buzzword in the question stem. We're asked to compare these 2 different groups, the patients with the lesion and the patients without. Taking a look at the answer choices, they're written in parallel form. So as we move into the plan for attacking this question, let's take a quick look at what's being compared in those answer choices. Each of the answer choices compares the total amount of time in sleep between the 2 groups, as well as the amount of time in REM sleep specifically. Well, we've already identified these trends. The patients with the lesion, the sick patients, slept longer in total, and they also spent more time in REM sleep, although they spent about the same amount of time in non-REM sleep. So let's match that prediction then to an answer choice. In this case, the correct answer is C. Again, the affected participants, the ones with the brain lesion, slept more total time. They also spent more time within REM sleep. Okay, so we've seen a table, we've seen a stacked bar graph. Let's look at a third representation of data in a visual form. So at this point in the group of experiments, the neuropsychologist gets a friend. He or she partners with a neurobiologist, and at this point, they're interested not in the amount of time spent in different sleep stages, but rather the levels of different neurotransmitters that exist during the different stages of sleep. And that information is summarized in Figure 2. So let's elucidate what you should look for when presented with a graph on test day. First, start by identifying the axes much as we did for the stacked bar graph. In this case, the x-axis is categorical. It's looking at the different sleep stages of non-REM and REM sleep. And the y-axis, while not specifically labeled, must be referring to the different levels of neurotransmitters. These must either be concentrations or standardized values, something to indicate the level of a different neurotransmitter. When units are presented, by the way, on a graph, make sure to take note of those units. Requiring conversions or misusing units can be common ways for the MCAT to design wrong answers. So after identifying the axes and, if present, the units on those axes, identify any points of interest. These could be maxima or minima within the graph. They could be zero values in the graph. If there are multiple lines, as we see here, the relationship between those lines and any points of intersection between them can be useful information. Looking at this graph in particular, we note that the two neurotransmitters almost seem to be mirror imaging each other. Whereas neurotransmitter 1 increases during the stages of non-REM sleep and then drops in REM, neurotransmitter 2 drops during the 4 stages of non-REM sleep and then increases during REM. Avoid over-interpreting this graph. Figuring out the identity of the two neurotransmitters here may be tempting, but unless we're asked about that in a question, it's not worth our time right now. So let's take a look at a question asked about this figure. In this question stem, we're given another buzzword. We're asked during which stage of sleep the difference between the two neurotransmitter levels is the greatest. There are a few ways we could approach this. One inefficient way of doing so would be subtracting each of the values in the graph to determine which one is the largest number. Because the answer choices are not numerical, they're referring to the different stages of sleep, this would be more work than is necessary. Instead, let's just look at the graph and figure out where the biggest space is between the two lines. We'll add some arrows to this figure to facilitate this process. Taking a look at these arrows, the question simply becomes, at which point is the arrow the longest? That would represent the largest difference between the two neurotransmitters. And in this case, the arrow is the longest during REM sleep. There's the largest difference there. You might have noticed that this graph is actually put together in a somewhat contradictory way. The trend in neurotransmitter levels would have been visually smoother if REM were on the left side rather than the right. This is not uncommon on the MCAT. Presenting data in a slightly obfuscated or unclear way can be a classic mechanism by which the AAMC can increase the difficulty of a question. Before moving on to the next learning goal, let's take stock of what to look for in tables, charts, and graphs respectively. In tables, start by identifying what the rows and columns represent, and look for any major trends across the table. Avoid over-interpreting every cell. For charts, start by looking at the axes, whether they're categorical or numerical, and again look for any major trends that exist within that chart. Finally, for graphs, start with the axes, taking note of what they represent, as well as any units if they're present, and then take a look at what's significant within that graph. These could be maxima, minima, zeros, points of intersection. If there are multiple lines, the relationships between them. So we've now taken a look at visual representations of data in 3 different forms and drawn some conclusions and determined what they represent. Now, let's go the other direction in our next learning goal. During this learning goal, we'll begin to identify and explain the relationships between variables, which will also give us an opportunity to define some of the terminology that's used to describe correlations. We'll also take it a step further. Once we've identified those relationships, we'll find an appropriate graphical representation of them. So if one of the major tasks of learning goal 1 was to take visual representations and draw conclusions from them, be able to describe them in text, then we're just reversing that process here, taking relationships that are described in text and converting them into a visual form. So let's explore this first study. Take a moment to read through this study and identify what's being investigated. Also, identify what the conclusion is of this study. We're given some key information in the paragraph. It's a scientist who's conducting the study, and what's being investigated here is the relationship between dopamine levels and mood. In this case, the conclusion is given as the last sentence. As described here, an improved mood is correlated with increased dopamine. What terms could we use to describe this relationship? Well, when an increase in one variable is correlated to an increase in another, or by extension a decrease in one variable being correlated with a decrease in the other, we could describe this as a positive correlation or a positive relationship. With that in mind, let's take a look at the first question in this learning goal and see how the MCAT might test this ability to discern and represent this relationship. So let's take a look at question 4. In this case, we're asked for the most appropriate representation of the findings from the study. The answer choices are all graphs here, with the x-axis being affect and the y-axis being dopamine levels. Affect and mood are not exactly the same thing. Affect is the emotion that one displays, whereas mood is by self-report. It's what somebody says they feel. But unless somebody has significant psychotic symptoms, usually affect and mood mean more or less the same thing. Which graph below demonstrates the findings that we had from this study? A positive correlation, that is. In this case, that matches with answer choice C. C demonstrates this positive correlation and is therefore the answer. But let's take a look at the other relationships. You wouldn't spend time doing this on test day, but it's worth going over some of the nomenclature associated with study correlations. Answer choice A demonstrates a neutral relationship. We see that as the affect level increases, there's no change in dopamine levels. Answer choices B and D both demonstrate negative relationships. In this case, as the affect levels increase, the dopamine levels drop, or as the affect levels decrease, the dopamine levels increase. While both of them are negative relationships, there is still a slight difference between these two graphs. B represents a linear relationship, while D does not. So we've seen how one relationship can be demonstrated on a graph, but let's take a look at more complex relationships and those between multiple groups. Take a moment to read through this study and again determine what's being investigated and what the conclusion is of the study. In this case, the patient population being studied are individuals with unilateral sensorineural hearing loss, and in particular, the investigators looking at their deficits, hearing deficits that is. The conclusion is again given in the last sentence, and in this case it's found that individuals with this hearing loss have a higher threshold at all frequencies than patients without this type of hearing loss. So there's a comparison going on between the two patient populations, and the conclusion that's been identified is there's an increased threshold for those with hearing loss at all frequencies. Let's take a look at how this could be represented visually. So in this question stem, we're being asked to find the appropriate representation of that data, and we're given 4 graphs that demonstrate these relationships. There are 2 parts to this question. The first, which may seem very straightforward but is an important first step, is to determine which line is which. In this case, the solid line, as we're told, represents patients with hearing loss, and the dotted line represents patients without this hearing loss. So what would we expect in terms of the relationship between these 2 lines? What was the conclusion that was given? The conclusion stated that individuals with this type of hearing loss have a higher threshold at all frequencies. So logically, we should expect that the solid line, that represents those with hearing loss, should be higher than the dotted line, those without the hearing loss. Which answer choice matches with that prediction? In this case, answer choice B is the only one that shows the thresholds always being higher for those with hearing loss, and therefore is the correct answer. Let's take a look at the other graphs, though, just to determine what the relationships are that they're demonstrating. Answer choice A demonstrates that the threshold is higher for those with hearing loss, but only at high frequencies. In fact, at lower frequencies than this point of intersection, we see that the dotted line, the patients without hearing loss, is actually higher than the solid line, so this cannot be the correct answer. For answer choices C and D, the threshold for patients with hearing loss is shown to always be lower than the threshold for patients without hearing loss, and this is the opposite relationship than was described in the study. When reading passages based on experiments, keeping the study in mind is always important. As the Kaplan tip on the bottom of your page points out, being able to determine the appropriate visual representation for data or relationships that are stated in a passage is going to require an understanding of what that study was trying to accomplish in the first place. Finally, let's take a look at one more way of representing a relationship in visual form, and this one's going to be a bit more difficult than the 2 we've done already in this learning goal. Take a moment to read through this study and determine what's being investigated, as well as the conclusions that we could draw. In this case, the goal of the study is given very clearly in the first sentence. A researcher here is attempting to replicate Weber's law for contrast perception. The conclusion is a bit less clear and will actually require us to interpret what's going on in this graph. To interpret this graph, let's use the same steps that we used in Learning Goal 1. Start by identifying what the axes are. In this case, the x-axis is intensity, and the y-axis is units of contrast. Then identify what's going on in that graph, what the notable characteristics are. In this case, we see it's a single line, but the curvature of the line should be what sticks out. What we see is that as intensity increases, the contrast increases, but at an ever-decreasing rate. In other words, to accomplish the same difference in contrast, we need to increase the intensity by larger and larger amounts. In other words, larger and larger intensity gaps are required to perceive that same change in contrast. With that in mind, let's see how they could test your interpretation of this graph on the MCAT. Take a moment to read through this question stem and, using the Kaplan method for science questions, bring yourself all the way to an answer. What is the most reasonable interpretation of the data in Figure 3? We've already assessed the question. We're being asked for the interpretation of Figure 3, so an appropriate plan here would be thinking about the relationship that's demonstrated there and then finding an answer choice that matches that prediction. The relationship we described is that as intensity increases, contrast increases but at a decreasing rate. The answer choice that best matches this prediction is answer choice B, and we identified this with the lines in the graph as well. To see the same contrast, a larger change in intensity will be needed at higher intensities. Now, we've already addressed the main takeaway from this question that has to do with the learning goal. We've identified and explained the relationship between these two variables, but there are a few more neat things to point out about this question. First of all, remember the purpose of this study, which was to replicate Weber's law. B basically describes Weber's law, so if you didn't recognize it, it's probably not a bad idea to go back and review in your behavioral sciences book what Weber's law states. Answer choices A and D essentially make the same mistake, characterizing this as a linear relationship, but we saw that wasn't the case in the graph. Finally, answer choice C seems very technical and scientific, but is actually kind of a silly answer. We actually made an interpretation while coming up with an answer for this question, so we know it is possible to interpret this graph regardless of its axes. Alright, so we've gone from visual representations of data to text, to explaining their relationships, and from explaining relationships to representing those relationships graphically. Now, in Learning Goal 3, let's take a look at using data like a scientist, similarly to how you will as a physician. During the last learning goal of this lesson, we'll now take data that's presented to us and draw conclusions from it. We'll also extrapolate from that data, predicting possible future events based on trends that we see. You will see questions on the first two learning goals of this lesson, but certainly this last learning goal is the most heavily tested on the exam. And that should not be a surprise. If medicine is a career of continuous learning, then the ability to take in new information, assess new research, and be able to apply it to your patients is paramount as a physician. After all, most careers in medicine are in excess of 40 years, and it wouldn't make a lot of sense for a physician now to still be practicing the same way that he or she did in the 1970s. So with that, we'll look at a few more experiments and see what information we can glean from them and then apply that in various questions. Let's go ahead and dissect this first experiment. What's being studied in this experiment are reflex times. And we're given a bit of the experimental setup in the second sentence. We're told that the participants have to catch a ball after it's been dropped. What's being measured is a bit interesting here. Rather than measuring the amount of time or the speed for that reflex to occur, the researchers actually measure how far the ball falls before the participant catches it, serving as a proxy essentially for how long the reflex would occur, making the reasonable assumption that if the reflex takes longer, the ball is going to fall a further distance. Let's take a look at the table and, using similar processes to that during Learning Goal 1, analyze some of the data that's been presented. The rows here represent the different participants, and the columns represent a few different criteria: the identity of the participant, that person's age, as well as their times in 3 subsequent trials. So let's identify what trends we can see in this table. First of all, we see something going horizontally, that as the trial number increases, the amount of time to respond decreases. And this is true across the board. All participants looking at all 3 trials have that same trend. Let's take a look at vertical relationships. So while there's no trend immediately apparent looking in each of the columns, if we organize these values by age, a trend begins to emerge. If we start at the lowest age, 21, and work up to the highest age of 30, we see that the distance generally decreases with age. In trial 1, this trend holds pretty neatly. As age increases, the distance decreases from 13.9 centimeters to 13.6 to 13.3 and eventually to 13.2. Trial 3, it also holds pretty neatly from 13.1 to 12.1 to 11.6 to 10.3. Trial 2, it's not quite as clean, but the trend still generally holds from 13.6 to 13 to 12.9 and Alright, so then the 30-year-old is slightly longer in that trial at 13 centimeters again. But certainly the trend more or less holds as we're looking through the table. There are two major relationships being shown. As trial number increases, there's a decrease in distance. And as age increases, there is also a decrease in distance. So let's see how they could test this data on the exam. Take a moment to read through question 7 and identify what your plan would be for answering this question. This is another question where the answer choices are written in parallel form, and that will help us quite a bit. They're actually looking for the two relationships we identified in the table. How reaction time, or in reality the distance that's being measured here, relates to the age of the participant, as well as with the trial or attempt number. The relationships we identified are that as age increases, reaction time decreases, and that can be described as a negative correlation. So we could immediately cross out answer choices A and B. They describe the relationship between reaction time and age as a positive correlation, which is an opposite answer choice. The other trend apparent in the table is that as trial number increases, reaction time will also decrease. And that's again a negative correlation, so we could remove answer choice C, and answer choice D is the correct answer. So this question looks at the conclusions we can draw from that table, but let's now extrapolate that data and make some predictions about future events. Take a moment to read through question 8 and identify what your plan would be for answering this question. The question identifies two important changes to the experimental conditions. In this case, another participant is added who is younger than any of the participants that have already been listed, and another trial is added to the experimental setup. An appropriate plan for this question would be to think about how the two trends we've already identified play out with these new experimental conditions. Let's start with age. The younger age of this participant would argue that we'd have a larger distance or a slower reaction time than the participants already listed in the table. Contrarily, adding another trial would argue that we'd have a smaller distance for this participant during that last trial. So how do we reconcile these differences? We aren't given enough information to determine which trend is a stronger trend, so we don't know if this last trial for this participant would be longer than that of other participants or shorter. This level of ambiguity may be kind of uncomfortable as a prediction, but let's see how that plays out with the answer choices. Take a moment to see if that prediction matches to any of the given answer choices. Here, that prediction actually works quite well for answer choice A. The two trends that are given here oppose each other, and we don't know which is stronger. Therefore, we don't necessarily know what participant 5's fourth trial is going to look like in terms of the reaction time. All of the other answer choices given here assume that one of those trends is stronger than the other, or that they cancel out perfectly. But again, we're not given enough information to make this determination, so the correct answer choice is actually the least definitive of the answer choices that is given here. This question is a great example of what the Kaplan tip on the bottom of your page highlights, that identifying trends is certainly an important part of data interpretation, but identifying those trends also requires you to think about what those trends represent and how those trends may work with or against each other, thinking critically about the data that's being presented. Alright, so let's take a look at this experiment, which was already presented in Learning Goal 1, although we'll be looking at a slightly different aspect of it this time. Remember that this study was identifying the relationship between a particular lesion in the brainstem and the amount of time that a patient spends in different sleep stages. 6 patients with that lesion and a group of control subjects were compared. We have a slightly different representation of some of the data we've seen before, and in this case it's given as a chart. What do you notice about this chart of sleep stage versus time? Well, the major conclusion that we can identify, which we already did before, is that individuals with the lesion spend about 2 times as long in REM sleep as those without. But take a look at the other information. We can see that the non-REM sleep stages are roughly equal. There are some slight differences here, but they're certainly not as pronounced as with REM. So let's see how the MCAT could test our ability to make a conclusion about this chart. Assessing this question, we see that the answer choices are long, logic-based answers. But the task is given relatively clearly in the question stem. We're being asked what we can conclude about sleep in these two patient populations. And we've already identified that there's a major difference between these two populations with respect to REM sleep, but they're about the same with respect to non-REM sleep. Now, that's a pretty good prediction, but these are long, logic-based answer choices. So let's use process of elimination to knock out flawed answer choices and arrive at the correct one. Answer choice A is flawed specifically because of the word each. The patients with lesions spend about 1 to 2 hours in each of the stages of non-REM sleep, and they spend over 4 hours in REM. If we totaled all of the non-REM sleep time together, that would be longer than REM, but that's not what answer choice A is stating. Answer choice B is a great trap answer because it sounds similar to our prediction. We recognize that patients with the lesions do spend about double the amount of time as patients without lesions in REM sleep. But there are a few flaws here. Certainly, the patients without lesions do not spend an equal amount of time in each of the non-REM sleep stages. They have some variance there. And they certainly don't spend double that amount of time in REM sleep. Specifically comparing non-REM 4 and REM with this patient population, those two bars are almost exactly the same height. So answer choice B, though similar to the prediction, does not match and is not the correct answer. Finally, answer choice C should be easy to eliminate. The bars in REM sleep, as we've identified, are not even close between these two patient populations, so there certainly is a difference between those two. Answer choice D matches very cleanly with this prediction. Indeed, the amount of time in affected versus unaffected patients in non-REM is about the same. Now, this is sort of an interesting question. While the most pronounced part of the graph is certainly the difference in REM sleep, this question actually chooses to ask not about that most important finding, but some of the other findings that are available in the chart. So what does this mean for you on test day? Well, you should still identify the most pronounced finding within a chart, graph, or table, but don't be surprised if when you hit the answer choices, they actually ask about a slightly different component or aspect of that data set. Indeed, this is representative of why it's important to be adaptable when you're using the Kaplan method for science questions. Finally, we'll continue this study again, and we've actually seen this same figure before. It was figure 2 earlier in this lesson. As a brief recap of the figure, we identified that the x-axis are different sleep stages, the y-axis are different concentrations or levels of these neurotransmitters, and that the two lines are almost mirror images of each other. Whereas neurotransmitter 1 increases during non-REM and then falls at REM, neurotransmitter 2 falls during non-REM and then increases at REM. So let's take this a step further than we did in Learning Goal 1 and make a prediction about the identity of those neurotransmitters. Take a moment to read through this question stem and identify what your plan would be for answering the question. If we assess the question, there's a great buzzword given here, glutamate. Whereas to identify which line within the graph would best represent glutamate's levels during sleep. Taking a look at the answer choices, like many of the other questions within this lesson, they're written in roughly parallel form. That means that an appropriate plan would be looking at the differences between these answer choices. Specifically, if glutamate is excitatory or inhibitory, and then if it's going to be increased or decreased in REM. Well, let's start with that first point. What kind of neurotransmitter is glutamate? Glutamate is a prototypical excitatory neurotransmitter. In fact, it's the predominant one used in the central nervous system. That information alone allows us to knock out two of the answer choices, and this actually leaves us with an interesting second step. We expected that the plan here would be to determine if glutamate would therefore be increased or decreased within REM, but actually both of the answer choices that remain state that it will be increased. The difference then between these two answer choices falls in the interpretation of the graph. We're now being asked to determine which neurotransmitter is increased in REM, and we can see that that matches here with answer choice D. Taking this content one step further, this answer choice should make sense. We know that glutamate is excitatory and that REM is a time of increased brain activity. In fact, the brainwave seen on electroencephalogram, or EEG, during REM sleep is very similar to the awake state. So it makes sense that the excitatory neurotransmitter glutamate should be increased during REM sleep, a time of increased activity. So let's wrap up this lesson with a bit of a review. First of all, a few action steps when presented with data. Anytime data is given in visual or text form on the exam, look for an overall trend that's being identified. Is there an increase in the data points, a decrease? Are they scattered? Are they close to each other? What are the trends we can identify within that data? And then if there's more than one data set that we're asked to compare, it's best to look for the differences between those groups, which often means looking for the widest gap that exists, as we saw on the neurotransmitter 1 versus neurotransmitter 2 graph. And it's always a wise idea to know what the graph, table, or chart is representing by looking at the axes and variables that have been identified. Data can be represented in multiple ways on test day. Thus, the way the data is represented can give a hint as to how the MCAT will ask you to interpret that data. More specifically, for a table, we'll often be asked to compare specific cells or specific trends that exist within that table. Line graphs are most often used to follow the progress of a variable over time or over some other variable, whereas bar graphs are usually used as comparative information. Pie charts, while we didn't look at them in this lesson, generally are used to identify the part of a whole or the relationships between parts that add up to that whole. Finally, the MCAT will frequently ask you about the relationships between variables as they're represented within a passage, chart, table, or graph, and this means identifying the correlations that exist between variables. Correlations can be described as positive, whereas one variable increases, the other also increases, or negative, whereas one variable increases, the other decreases. There could also be no correlation or a neutral correlation between variables, where an increase in one does not predict an increase or decrease in the other. Correlation should not be confused with causation. Two variables can be related to each other, but that does not necessarily mean that one causes or is a result of the other. And indeed, to actually prove causation, one needs to demonstrate that relationship through a lot of experiments. Finally, relationships need not be straight lines. Indeed, an exponential relationship will be one where as one variable increases, the other increases at an increasing rate. In other words, there's a curvature upwards. Whereas a logarithmic graph would be one where an increase in one variable is correlated with an increase in another variable, but at a decreasing rate. In other words, usually a curvature downwards. Congratulations on reaching the end of this lesson. We hope that with this introduction to Skill 4 questions, those that test data-based and statistical reasoning, or data analysis for short, that you recognize that the MCAT tests not only your content knowledge, but also some of the other skills that you'll be using as a physician. So as you continue to practice these questions and improve on them, so too will you be arming yourself with some of the skills to be a modern, up-to-date physician who's in the know when you treat your patients. Thank you very much for watching, and good luck on your exam.